we have our n plus one numbers of data point, then what we can do, we can select a polynomial of nth order in general, just to so that that polynomial will be passing through those data points, interpolate the value. Using a direct matrix calculation or using some technique of solving this problem is a bit elegant. We switch to another technique that avoids the solution of simultaneous equation, that was the Newton's divided difference formula, where a table can be formed of divided differences. Then we can calculate the unknown coefficient associated with the interpolating polynomial. But another similar technique that avoids the calculation of divided difference is Lagrange's polynomial. And this is not that much different from Newton, but let us discuss on it. Can you see this share?
Yes, sir.
So this is your Lagrange's interpolation polynomial. As you know that any, if we have points, or data points known to us, then we can find a basis functions so that this function will satisfy those points. As a result, any intermediate point that is not known to us can be calculated from that polynomial. In general, the interpolating polynomial can be expressed by equation 18.20, where fnx is equal to sum I equal to 1 to n. N is the order of a polynomial. Depending on the order of our approximation, we will fix n, and accordingly, the Lagrange's polynomial basis function Lix will be determined. How this can be there? Let us discuss about a very fundamental something from where you will understand how the Lagrange's polynomial actually came into being. So in this case, let me share our whiteboard, and I will let you know how to find a linear polynomial with the help of Lagrange general formula. Very simple. You can also do it by your own. Let me fix it out because I have something to set. It's very difficult to conduct everything from home because we have many constraints here. Okay. Let us consider about linear interpolation case that we discussed for the case of deriving the Newton divided difference formula. If you have two data points x1 and x2 are available, and the corresponding value of your function is say f1x and f2x, fx2 let us call it. This function a linear function, so we are using order 1, the value of your function at x1, and similarly the value of your function at this point is equal to f1 x2. Now, what we have done earlier, that if we assume that these 2 points are actually, if we have only 2 points, then a straight line can is actually the polynomial that will satisfy these 2 points or pass through these 2 points. Then what will happen if we know the equation of this straight line? Then what we can do, if we have any point there x whose value was not known to us, we can extrapolate this value or now interpolate the value from this function. Okay, then how the equation we derive from the very basic geometry, just shoot a similar triangles are there. Then you find the height and base ratio, isn't it?
Yes, sir.
It is equal to what? Your height is, for example, you can consider f1 x1 fx minus f1 x1 x minus x1 is equal to f1 x2 minus
F1 X1
f1 x1 divided by
X2 minus
x2 minus x1. Okay, you can easily convert this formula. Okay, we are finding the equation of this straight line. Let us put a subscript there, f1, that will tell you that it is your first order type interpolation. Then our objective is we have to solve for f1x, and by putting the value of f1x within the range x lies between x equal to 1 to x2, we can interpolate the value, isn't it?
Yes, sir.
If we want to solve for f1x, after just few lines of algebra, you can easily express this quantity as x minus x2 divided by x1 minus x2 multiplied by f x1 plus x minus x1 divided by x2 minus x1 into f1 x2. Just you rearrange this equation and put it into this form. Why we are putting into this form? Okay, it will resemble the general expression of your Lagrange's polynomial. Okay, what you can do, this can be written as actually say L1 into fx1 plus L into fx2. Can we write this? Where L1 and L2 are the basis function. Here in this case, your L1 is equal to what? X minus x2. Of course, these are the function of x divided by x1 minus x2, and L2 is equal to x minus x1 divided by x2 minus x1. Okay. So this is your first order Lagrange's polynomial. Now, what is the nature actually of L1 and L2? This is very important. Okay, if you see that our L1 was equal to what? Our L1 was x minus x2 divided by x1 minus x2. And L2 is equal to x minus x1 divided by x2 minus x1. Okay. If we want to plot these two functions in x, and that how they related. Okay, you see that originally our 2 points were there. One was at x1, another was at x2, and this is the value of your function. We can consider that this is the straight line whose equation we have derived, and that equation equal to f1 x. And if we want to plot L1 and L2 on top of this figure, you see that if you want to plot L1, the red figure, you see that at x value of L1 at x equal to x1 is equal to what? Is it not 1?
Yes, sir.
And
Yes, sir.
value of L1 at x equal to x2 equal to what? Is it not 0? Similarly, you see that your value of x at x is equal to x2 is equal to 1. And the value of L2 at x is equal to x1 is equal to 0, isn't it?
Yes, sir.
So you can plot that this curve is actually, this is your L1. And if you want to plot L2, then this is L2. And if
Yes.
we weight them with the corresponding value of, if we weight L1 with F1 X1, and if we weight L2 with F1 X2 and sum them up, then you will get that straight line. Okay. So in this way, we derive the interpolating formula. And if you want to find a value intermediate between these two, then we can easily find the equation or value or interpolate the value of our function accordingly. So this is how your Lagrange polynomial is extended, is derived. But if we extend this polynomial for higher order cases, let us see what is there in your book. So the, your 18.20 is the general equation for your function. Depending on the order, the term of your interpreting polynomial will be settled. And your L1x is equal is a product of some functions of this type. You can verify it for putting I equal to 1. If we put there, then you will see that it is the equation that we have already derived. This is the first order or linear polynomial for n equal to 1. And if we set n equal to 2, we will have another polynomial there, something like this. You see that in this case, how many points you will need? Because
Sir,
this is similar to quadratic type fitting. Okay, in this case, you need 3 points, isn't it?
Yes, sir.
Value of function at the 3 point will be equal to f2x1, another will be equal to fx2, and another is x3. Or whatever designation you can do that. And you see that the nature of your behavior of your polynomial is nearly same. Okay, at the first term, in your first term, what is happening there? If for the case of second order, in this, if we put x is equal to x1, in your now the designation has been changed probably. For this region, our 3 points are x0, x1, and x2, are not they?
yes, sir.
If your x1, x2, and x0 is there, when I derived the equation, I used x1 and x2. So you can easily change the subscript to coincide with those equations. So these 3 points are there. Your first term should have a value equal to, say, this, consider this is L1, this is your L2, and this is your L3. So L1 will be equal to 1 at x equal to x0. If we put x equal to x0 there, would it not be equal to 1?
Yes, sir.
It would be equal to 1. If we put x equal to x2, is it not equal to
Zero,
x
sir.
equal to x equal to x1? It is 0, isn't it? Even at x equal to x2, it is 0. So this L1 has a maximum value equal to 1 at x equal to 0. Same reasoning is there for this equation. Okay. So you can devise a shortcut technique to memorize the thing. But if you want to have higher order type polynomial, you can use that general expression there with 18.21. Lix is equal to, because j cannot be equal to 1. If your j is equal to 1, then your denominator would be equal to, for example, what will happen for I equal to 1 to n? If you j equal to 0, then it will be equal to 0, infinity. Or we actually, for our practical purposes for hand calculation, we rarely use order greater than 2, okay? Because if you want to increase the order, your hand calculation calculator will not enough. You have to write do this, okay? So this example is there for your first and second order cases. So if you want to first order approximation, then how many points we will need? We will need only x0 and x1, isn't it?
Yes, sir.
If we need x0 and x1, then this value will be with us to find the interpolating polynomial. Then if interpolating polynomial is available with us, then we can find the value of our function at any value of x that is lying between 1 to 4, okay? Isn't it? Can we go beyond this interpolation? Because your equation is derived between the and valid for between these two intervals. So in this case, you have been asked to find the value at x equal to 2. So in your equation for linear interpolation, you put the value of x equal to 2, then this is what you value, okay? As true value is not available with us, we cannot calculate the absolute error. What you can do in order to what we call relative accuracy,
Approximated.
if we want to find the relative accuracy between the performance of the algorithms, then you can calculate the same by using Newton divided difference, then you can compare the result. But for the first order case, you see that Newton divided difference and Lagrange's polynomial are same. Difference will be there for higher order cases, okay? So if we increase the number order and try to interpolate the function, you will find how the order of the function improves the order error. But here you see that you cannot use the absolute error, okay? Yeah, true error, because true error are not known to you, okay? The way these three, for example, in our straight line case, we have in the first order approximation, we used L1 and L2 and describe the nature of L1 and L2 there because they have the value equal to 1 or passing and other cases are 0. Okay, the same thing is there for the higher order polynomial. This is also depicted in this figure. You see that each of your term will be passing through a point, but if we add all these terms together, then you will a polynomial. That polynomial will be passing through all the 3 points involved there. This is illustrated for a quadratic or second order case. This pseudo program is there. You can write the program to do this. Okay, this is what your Lagrange interpolation formula, and we can easily implement it, and we can calculate it for our purposes. Another issue is that for our exam purpose, actually, we will not be going beyond second order. Okay, your calculation will be limited to second order for written exam, and if you want to have some quizzes, it will be limited to first order. So the reason is that general solution is a bit difficult to put into LMS if we are order is very high, or not very high actually, even if the order is greater than 2. Now 18.3 coefficients of an interpolating polynomial. We have discussed this thing at the beginning of the chapter, that if we have our polynomial, that polynomial can be, what is it? A message is coming. What is that? Although both your Newton and Lagrange's polynomial are suited, but all these polynomial actually can be represented by a general form. Is it not the general form 18.24 that we discussed at the beginning?
Yes, sir.
Yes, sir.
So in general, what is the technique of finding the coefficient a1 through n? Is it not that if we have our n numbers, n plus 1 numbers of points, then we can put this there, because in this case, you see, we have a constant term there, isn't it?
Yes, sir.
If we have a constant term there, then our index is n. So actually, how many unknowns are there in our equation?
N plus 1.
N plus 1. So if n plus 1 equations are there, then how many data points you will need?
Uh,
You see that in this case, how many numbers of a's are there?
sir,
A number is n plus 1.
N plus 1. Yes,
So
sir.
then you need n plus 1 equations to find the value of your n plus 1 unknowns. In this case, you need n plus 1 data points. Okay, each of your data point will be satisfied by this equation. Then you will have n plus 1 numbers of simultaneous equation. You can solve them to find the value of a's. But what I have discussed earlier, this type of matrix or simultaneous equations are not easy to be handled. For this reason, it is rarely we use this general approach. Then for if they are given in some point x0, x1, x2, something like this, then we do not know the value between, for example, say x0 to say x1 in this interval. So in this case, what we can do, we can find a polynomial f and x, and in that polynomial, we put the value of x, say this x equal to say x prime, we need to find the value, then put the value of x prime there, then you will find a value, isn't it? This is what the interpolation. Now, if we want to go in the reverse way, what will happen? Reverse way means what? If we change the axis, for example, in this way, that means you have your fx value known, then you need to fx value of x. What you can do, you can just
X.
change the axis, then you can proceed with finding the, okay, your general logic can be something like this, okay? That if we interchange the independent and dependent variable, and we proceed with calculating the interpolating polynomial by using the technique that we discussed, it may work, okay? But the problem is, in most of the cases, the point that we are considering, they will be equidistant. That means the difference, that means they will be sampled at a constant sampling interval, okay? As a result, the distance between these two will be same, isn't it? If we consider it del x, the distance between two successive data points in independent variable is same. We call it equidistant, isn't it?
Yes, sir.
These are equidistant. But will your fx be equidistant? In general, not.
No, sir.
So then what will happen then? If we change the axis, that is swap the variable, you make our independent variable dependent and vice versa, that will create a problem that your independent variable would not be equispaced. Even in some cases, it can be multi-valued, something like this. Okay, multi-valued means what?
We will have
It is
two.
not it is not monotonic type. That means if you have a function something like this, then how will happen for any a function value, say fx, for a particular function value, you may have two values of your independent variable originally present. that will have this thing. So multiple something can be there. Okay. So these are the problem actually that in inverse interpolation we used in higher order, for example, research or analysis. In such cases, what you can do, one remedy of this problem can be, say, you can, what you can do, you feed this curve, okay? For example, without using your interpolating type algorithm, you use your curve fitting technique, okay? In your curve fitting technique, we have our x and fx values given. Using those f and fx value, we can find a least square curve, okay?
Yes, sir.
Isn't it? Least square error curve. If that curve is available with us, then we will find an equation there. Let us consider that this is your fitted equation fx. Our condition is what? If your fx will have certain value, say that fx is equal to, say, a, you need to find the value of x at which your fx is equal to a. Now, how can we do that? Is it not a root finding type problem now?
Yes.
That means you can set your equation fx minus a equal to 0 and solve for x, isn't
Yes,
it?
sir.
That will give you the value of x at which the fx value is equal to a. So in this way, we can avoid the problem of inverse interpolation. So in the case of inverse interpolation, one bottleneck is what? If we swap the independent and dependent variable, your independent variable originally was equidistant, but your dependent variable in general not equidistant. But if you swap the variable, actually, then your independent variable becomes dependent variable becomes independent, and it is not equidistant. And in many cases, maybe multi-valued. For this reason, what will happen? This will not work. So for this, one remedy of this thing can be the, or we have some other approaches also for interpolation. Okay. Actually, incremental search technique is one of the mostly used simple technique if we have huge number of data points with us. This is simple, okay? Your first order Lagrange interpolation can be deployed between 2 points, and we can easily find the interpolated value with lesser error if we have sufficient number of data points. Now the thing is that because we do not need to devise, for example, a higher order polynomial there. But if we have, in such cases, inverse interpolation can also be made. But if we have our equations to be derived in this way, then one remedy is what? You apply your curve fitting technique there. Then after having your curve fitting technique applied, you will find the equation that will best fit your observation. Then later problem will be what? If you have a function value given, then you need to find the value of x. Then your problem will be again going to another class we call root finding that we have already discussed. Okay, any one of the root finding technique can be deployed there just to find the value of the x that corresponds to that function value. This is an approach. Another technique is there. Another issue is also there. Okay, you see in your book at the beginning of our curve fitting technique, we have discussed about some functions that are non-linear, but that can be transferred into linear form by changing the variable. That we can apply our linear regression technique there to fit the curve. Or at the last stage, we discussed that you can use computer algorithm just to find the value of your unknowns if we have our linear type interpolation. Even we can use Newton-Raphson technique there just to find the coefficients of our fit curve using some iterative technique. Okay. Now, if we have our interpolation type problem and your function may have higher order nature, that means it very higher order type function, then this interpolating algorithm actually that we have discussed will not be working very nicely. The reason is that, okay, do you have another book written by the same author to you, Applied Numerical Method with MATLAB? The second reference I have given to you.
Sir, I don't think we have.
Sorry?
I don't think we have.
If you don't have, please try to download it, okay, from somewhere. As your library
Oh,
is not accessible,
okay, sir.
then
Okay.
I cannot suggest you to go to the library. But some older versions of this book is available in the internet, Applied Numerical Methods with MATLAB for Engineers and Scientists, written by the same author, okay?
Okay, sir. Okay, sir.
So in this book, you go to chapter 7 of your third edition, then chapter 17, okay, where you will find few additional something there at the end of the chapter. I will suggest you to explore the thing by your own. And you will find something there surprisingly that many of the programs that you are practicing is already there. Okay, you can also use them, okay? It will help. Okay, for example, in your lab classes, didn't your teacher refer to you some lab text related to your numerical analysis?
Sir, not yet, sir.
Not yet. Then we are in the sixth week. Then when it will be done. So try to collect that book. Okay, Applied Numerical Method. The second reference of your probably I have given the thing to you in your course plan, isn't it?
Yes, sir.
You try to find the book, Applied Numerical Methods. Are you seeing this book,
Yes, sir.
Applied Numerical Method? This is what the first page of the book, okay?
Okay, sir.
Okay, now we will be discussing okay, some case studies are there. You can take a look of the case studies of different disciplines. Or solutions are already given there. You can redo it just to get some insight about your technique, okay? Oh, I am going back. Okay, now another important technique of interpolation is spline interpolation. Okay, this is actually a very important but a bit complicated advanced technique of interpolation. A modified version of this interpolation technique is actually deployed in the graphics software, even in OpenGL. Okay, you will they use this spline type interpolation or Bezier curve there just to draw the smooth curve or find the interpolated value there, okay? Your spline means, do you know what do you mean by spline? Spline is actually a chord like something, okay? In our earlier days when computers were not available, we used to draw our graph by using graph paper, isn't it?
Yes, sir.
Probably you have also done the thing in your school life or college life, isn't it? In the laboratory,
Yes, sir.
if your
Yes, sir.
teacher asked you to draw graph, you used a XY plot, then you plotted your curve in the graph, isn't it? Then how did you connected the point of your observations?
So freehand.
It a freehand, isn't it? So in your freehand, what we usually do, we have a tendency, for example, to draw the curve so that that curve will be passing through all the points, isn't it?
Yes, sir.
And that eventually For example, if we have a graph paper XY and your data points are something like this, your tendency what? You want to draw a curve something like this, isn't it?
Yes, sir.
Actually, this has meaning, but practically, if we know the behavior of the independent variable with the dependent variable, that's why actually we try to use least square curve to know the trend, how close it is going to our what do you call, uh, because in most of the cases, actually, the behavior of x, fx with respect to x will be known to you. Otherwise, you cannot proceed with doing a practical thing. But in the case, okay, when we use the graph, actually, you see that it depends. It is very subjective case. Okay, if you have these 3 points, some are drawing the graphs in this way, some are drawing in this way. That means there are many possibilities that how this smooth curve can be drawn by freehand, isn't it?
Yes,
For this reason, in earlier days, for article engineering work with large volume, we actually we have some professionals to do this. We call them draftsmen. Have you heard the name draftsman? Still, this position is there. Okay, draftsman is actually a position who actually, if you give them the data, they usually draw the figure. Okay, not only the figure, even drawing. Okay, for example, in your first year, you obtained, you attended a course CE. What was the content of our course? Wasn't it civil engineering drawing?
yes, sir.
Yes, sir.
In your civil engineering drawing, what have you done?
We have sketched the different angles of the buildings,
Different views.
different views.
These views are actually not civil engineering drawing. These are the mechanical engineering drawing. Okay. In the civil engineering drawing, they usually draw the plan of a layout of a building or something like this in general. Okay. Even views are also there. Yeah, because they usually draw elevation or something like this of a building. Okay, that means, for example, say if you have an object, that object is something like this. Okay, that object is something like this, and you have a hole there in the object. Okay, it is going all the way to the next plane, something like this. Then if someone will ask you that you draw, you look through the front side, look through this side, look through top, look through the back side, then what will be the picture? Then they all are two dimensional, isn't it?
Yes, sir.
Yes, sir.
Then this is needed. The reason is that in most of the cases, if you want to draw an object and you want to send it to a company to build for you, they will not understand this figure. Actually, what you need to do, you have to prudently draw the sectional views, okay? With proper dimension, then they can easily assemble them together to find to build the object for you. In our case, okay, I don't know to what extent you have learned. In our engineering study in undergraduate level, our first year course was same for all discipline, civil, mechanical, and electrical. All engineering students should go through the same course in the first year. For this reason, we used to have some extensive training on civil and mechanical engineering, drawing, wood workshop, foundry, everything. So still I can draw some mechanical figure. Even the mechanical student probably will hesitate to draw. For this reason, actually, these are the part of the engineering. Okay, whenever you are doing something experimental, going elsewhere to do something, you will not find many people around you to help you. You have to be self-contained. Okay, for this reason, actually, the basic things are always we usually try to instill to the student so that he will not need, for example, the help of the professional always. The basic thing he can proceed with by his own. Okay, the draftsmen actually at that time they usually draw the engineering figures. If we have our huge numbers of figures that needs a professional task, they use a code like something in drawing this thing. Okay, what is that code? Okay, your cord will be looking like a strip of ribbon, okay, something like this, but semi-rigid type. So that if you have 3 points there, you can bend this ribbon in such a way that it will generate a smooth curve. Then you can draw a pencil, you can use a pencil to draw the contour of the curve, okay? This is called actually a spline. Now, how this can be mathematically replicated? That is what the content of spline type interpolation. Okay, we have many different types of spline. Okay, in general, physically, we have this ribbon. This ribbon can be shaped into the form of a straight line. It can be shaped into the form of a quadratic curve. It can be shaped for a higher order curve. Not only that, this ribbon cannot be shaped in a way so that at one time it will be going through all the data points. If you have 3 data points, you can find and explain there that will best fit this scheme. You may have some other data points there that the same spline can again be shifted there, but its curve will be different, something like this, okay? As a result, the spline that we are using actually piecewise spline, okay? It is piecewise. That means you have your intervals of data. By using each of the interval will be represented or by or featured by a different or same type of spline, but the parameters of your spline will be different. Okay, for example, you may have a straight line. That straight line slope and intercept will be different in different interval of your data point. Similarly, if we have a parabolic curve, that parabolic curve will have different types of parameter. We know the parameters of a parabola that will be different for different interval. Okay, this is there explained, but this is actually computationally by using hand calculator. It is very labor intensive, I would say. For this reason, we'll be giving some introduction only using linear and quadratic. So in the linear spline, type, what is our logic then? We'll be using a pitch of a straight line for each of the intervals of our data points to represent or to use as an extra interpolating polynomial. Okay. So now my question is that in this case, what will be the interval length? Because we need to draw the straight line. That means we need 2 data points, isn't it? To draw a
Yes.
straight line. So in this case, what will happen then? You have your, for example, if we have our data points, n numbers of data there, we are defining the interval in this way. This is one interval, this is another, this is nth interval. Then, is it not the equation of a straight line?
Yes, sir.
Yes, sir.
Okay. Then in this case, you can consider your f0 as your intercept, and you can consider this f as your slope. Can we calculate it with the help of x0 and x1 at the 2 extreme points?
Yes, sir.
Okay, we can easily calculate it. For example, you can put your x0 there, that with the help of x0 and x1, we can easily find what will be the value of our m0, and the next interval, it will be equal to m1. Your m1 and m2 will not be same, okay? They are not, m1 and m2 are not equal. The reason is that if you have your data, for example, say we have 3 data points, something like this. Then we have a straight line segment there that is defined by x0 and x1. We have another straight line segment there that will be defined by x1 and x2. Are the slope of this, is the slope of these 2 lines equal?
No, sir.
No,
No.
sir.
But you see that we have some point there. That particular point x1 will be satisfied by this segment as well as by this segment, because this is the interface between 2 segments, isn't it?
Yes, sir.
So at the interface point, but the problem is that this interface will not be, this interface is called knot. Okay, this is the knot of your spline. Knot, that knots are actually not smooth. If they are not smooth, then what will happen? There will be some problem if you want to take the derivative of the function that sometimes needed. you see that if we have a function, I don't know whether you have learned it in the case, because very elementary something, okay? Consider that we have a situation something like this, a triangular curve. This situation and that situation is very similar in terms of the thing that we are discussing. You see that if we have a function, for example, x t with respect to t, can you tell me if we take the derivative of the function, what will be the shape x prime t with respect to t?
It will be second order curve.
Second order, after derivative, it becomes
Oh,
second
Sorry,
order.
it will be a straight line, sir. Along
Sorry,
the
sorry, it will be
t-axis.
straight. Sorry, 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 sorry.
It will be a straight line along t-axis.
Along tx is a complete straight line, something a straight line, a straight line, a straight line, something like this, a straight line, something like this.
Yes.
Can you justify your answer?
So one would be straight line at the top and one would be straight line at the bottom. It's the negative axis.
It is very simple something. You see that the slope of this line is positive and the slope of this line is negative. And the switching of the sign of the slope is occurring at this point, isn't it? Say consider the t. At point t, say at point t, at point t, your slope is changing from positive to negative, okay? Taking derivative of a function with respect, if it is a straight line, with respect to the independent variable, is it not the slope of the line? If we have our y equal to mx plus c, if we take the derivative dy by dx, is it not equal to slope?
Yes, sir.
If it is slope, then that slope is constant, okay? It is constant up to this point, and it is positive. And at this point, you see that your slope is going negative abruptly. Okay, this is a problem of abrupt changes of slope at the point of the knot. Another issue is that if we in some cases we may need to further take the derivative of this function. If we want to take the second derivative of the function, can you tell me what will be the result?
It will be 0.
It will be 0. So you guys, when you answer something, you do not try to reason it, okay? Try to reason that whether it is 0 or not 0.
Sir, here the slope is constant. Then, sir, if we just take the derivative of a constant, shouldn't it be 0?
That is why I'm asking you that why it is, would it be 0 always, all the way? Hey, is there anybody in your section who can speak? Only 2 or 3 guys are always speaking. The others are doing what? If you cannot respond quickly, okay, from now, this is the last day I am allowing you to record my lecture. This is the last day I am allowing you to record my lecture. If you cannot respond quickly, okay, I am asking question, only 2 or 3 boys and girls are taking part, others are simply lying. Would this slope will be always equal to 0? Your curve
No,
is
sir, no,
something
sir.
like this.
In the knot point,
So
sir,
I
the
think when
derivative will
the
be infinite,
slope
sir.
is changing from positive to negative at that point.
Exactly that. At this point, you see that if we have a step change occurring there, that
Impulse
step
function.
change is occurring means what? We are having a change of the function, but that change is occurring almost at 0 time. So if we have a change of function del x, that is understandable. But if you have that change is occurring at a time, that time is tending is equal to 0, then that ratio will be equal to what?
Infinity.
Is it not
Yes.
infinity?
Yes, sir.
That
Yes,
means
sir.
you will have an infinitely like something derivative there that you cannot discuss with. This situation occurs in many stages of our practical life. For example, If someone will say that we have an alternating current, this current is sinusoidal in general, but by some reason, if your current is has changing in this way, okay, and changing your voltage, current is changing abruptly at that point, and you have in your home, you have some equipment that has inductor, and that this current is passing through the inductor. What will happen? Hey, first year এগুলো যখন
Sir,
ইন্ডাক্টর পড়াইছে টিচার, ক্যাপাসিটর পড়াইছে, তখন এগুলো পড়ায় নাই।
স্যার নেটে অনেক প্রবলেম করতেছে স্যার, আরেকবার যদি একটু রিপিট করতেন স্যার।
আপনার ভয়েস একটু ল্যাগ করছে স্যার।
ভয়েস ল্যাগ করলে then you could answer a bit later if you can hear me. Am I not hearable to you?
স্যার ঝিঝি মানে একটু স্যার কেটে কেটে আসতেছে স্যার কথা স্যার।
কেটে কেটে আসলো, এতক্ষণ ধরে কেটে আসলো না, এখন কেটে আসতেছে।
স্যার এখন স্যার ঠিক আছে স্যার, একটু স্যার আবার রিপিট।
Okay, what was my question? That, for example, consider that this is what the ideal shape of current alternating. Is it okay?
ইয়েস স্যার।
ইয়েস স্যার।
So by some reason, that curve is having a problem at that point, okay? At that point, a sharp rise is current is going to again decaying out in this way, okay? And similar thing is happening there. You have a load in your home that might contain an inductor. Can you tell me what type of electrical load contains an inductor?
Sir, air conditioners and then inductive heaters.
Air conditioners, inductive heaters. How many of you have inductive heaters in your home?
I have, sir.
You have, okay, fine. Then can you cite some other simpler example than this? Okay, try to explore it. Let us consider that your home contains an inductive load, something like this. Even a capacitive load can be there. So in this case, what will happen then? If we apply this current there in this inductor?
Sir, it will resist the abrupt change of current.
Okay, try to find the answer. It will change, resist the abrupt change of current. Okay, because it is not my responsibility to grasp the thing. Everything's are there in the book. You guys, you never, for example, study your text. You are very much happy with what your teacher is saying. You do not want to move an inch further by your own. In this way, engineering cannot be learned. Be careful about that. Things are changing every second. Whatever thing you are learning after, when you will graduate, 90% of it will be going obsolete. So this is the equations of a straight line. We can easily find the segmental ways, the equation of the straight line. But the problem is that we have our knots there. Those knots will have some problem because of sharp changes of the slope there with discontinuity. That might create problem for further calculation. So in order to avoid this thing, the avoidance principle can be just we can have some smooth, for example, situation there. This all the situation is described in this figure by changing the order of your spline. Okay, your spline can be of this different shape in such a way that it will minimize the discrepancy of your prediction. So for your straight line spline, your general slope will be this mi. You can put your coordinate there or the data point there that will give you the slope of the straight line. Then once the slope is known, Then you can interconnect the intervals. Then by using the spline, linear spline of a particular interval, you can predict or interpolate the value for that particular interval. Is it okay?
Yes, sir.
Yes, sir.
So this is the figure of the spline that I have asked, described already. Okay, you see that a ribbon is there, some pins are there. Okay, so you can shape your spline in such a way that it will coincide with the general behavior of your data points. So this is your straight line spline example. This example is there already. We studied with how many data points we have. We have our four data
Four.
points, isn't it? Then how
Yes.
many straight line we will need? How many data straight line we will need for 4 data points?
3, sir.
You see that the end point, we have our end point and a starting point, isn't it? This is your first point. This is your second point. This is your third point. And this is your fourth point, isn't it? Then how many segments we have? Interval, we have this interval. We have this interval. And we have this interval, isn't it?
Yes, sir.
Yes, sir.
Then how many data points we will need? Straight line we can have
Three,
this
sir.
Three straight lines.
there, isn't it? Okay, fine. Then by using the general formula of our slope, if we know the coordinate of these 2 points, can we
Yes,
calculate the
sir.
slope?
Yes,
So
sir.
all the slopes can be calculated, but at the knot points will satisfy both the equation connected by this knot point. Okay. Then if you are asked to calculate the interpolate the value at a certain point here, then you have to use this equation. If you are asked to calculate the value here, you have to use this equation and so on and so forth. Okay, in this way you can proceed with many numbers of data points. This is actually very easy to be implemented by using computer and give fairly accurate results. If we have many numbers of data points, that means interval size is small. Now the question, now the thing is why? Why the pen is not working there? Okay, let me start it out. Something has gone wrong.
Sir, I think you might have deselected the hand tool. That's why it's not working.
Sorry.
On the top left of the screen, there is a hand tool. I think you have deselected it. That's why it's not.
That hand tool.
Yes, sir.
Yeah. It was in a comment mode probably. Okay. So the extension is what? Quadratic splines. Okay. Quadratic means what? Second order, isn't it? Then in order to use second order spline, how many points you will need for a particular spline?
So minimum 3.
Minimum. So you will need the 3 points there, okay? So, but the technique is actually nearly same. Here in this case, many equations you will have to be solved, okay? The reason is that each of your data points should be connected together, isn't it? For example, when a first spline ends, a second pitch of the spline will begin. We will have an interface between the splines, okay? So at the interface points, the data point should satisfy the adjacent polynomial, okay? In the case of a straight line, it will satisfy the straight line. In case of polynomial, it will satisfy the polynomial. the general derivation is there. Okay, we can have a polynomial equation of the quadratic form of equation 18.28. Derivation is so straightforward that I hope if you cannot read, you will understand that thing by your own. Okay. So now the thing is that the function values of the adjacent polynomial must be equal at the interior nodes, isn't it?
Yes,
Yes.
sir.
Consider one. The function values must be what? Equal at the interior nodes, are not that, because nodes are there in the interior points, okay? Not the nodes are there where two pieces of polynomials are joined together, isn't it?
Yes,
Yes,
sir.
sir.
Okay, then the first and the last function must pass through the endpoints, isn't it? If we have our first polynomial or quadratic function that is valid for first interval, then the starting point must satisfy, it must satisfy the starting point, isn't it?
Yes, sir.
Yes, sir.
Similarly, the last equation will satisfy the last starting point. Okay. In the course of discussion, you will see that we'll need around we'll have around 3 into n numbers of unknowns. Then you have to find the ways to find 3n equations, otherwise they cannot be solved. So by using interior nodes, we will have twice n minus 2 conditions. You need not to verify it, just try to know the steps, okay? Then again, we will have endpoints there. In the endpoints, we will have 2 additional conditions there. The resultantly, we will have 2n conditions, okay? With these 2n conditions, we cannot solve for n unknown, 3n unknowns. Then we need another set, okay? This set is actually calculated by using this continuity equation. It is called continuity, okay? The first So if we take the first derivative of the interior nodes, then we can make them equal. Then we will obtain the general equation 18.33. This will eliminate add another set. Then fourth point is assume that the second derivative is 0 at the first point. This is actually is not very general, okay? Sometimes it is selected arbitrarily, but in this case, this is a good choice because it has been proved that if we set this in this way, it will best fit our curves. So you have your 4 conditions that we need to find, okay? Example will be there, you will understand it very clearly. Number 1, your adjacent what you call the interior node points, the 2 adjacent polynomial value must be same. Second thing is that the end and the starting and end point will give you 2 more equations. Then if we derivatives are equal at the node points, then this will give you some equation there at the node. Okay, if we have our n numbers of nodes, then how many interior points we will have? N minus
N minus 1.
n minus 2, because
2.
we have our first point, we have our last point to be eliminated, okay? Then we, as fourth condition is that assume that the second derivative is 0 at the first point. So having this thing applied, you will find the number of equation that is equal to the number of unknowns. Then we can easily find the unknowns. Then you will find the spline equations, and extrapolation, interpolation can be possible once you know the equations. Okay, this is using this example. All the process have been illustrated here. I hope you will understand it. You see that what you need to do first. First thing is that we have to write the equations for, we have to write 4 data points are there in the interval. Then we have to insert the data points there that will give you our equations, upper 2 equations, then lower equations can be obtained by the first and last equations. So initial and final values can be applied there to find the additional 2 equations there. Then if we derive the continuity of the slope, then by using that continuity, we will have another 2 equations. And if we set a1 equal to 0, 0 because first derivative, second derivative at the end, first point equal to 0, that will give you a1 equal to 0. If all the equations there, you can easily identify how many variables are there. They can be put into this matrix form. Can you imagine that what is the size of the matrix? Because we have our, how many unknowns? 1, 2, 3, 4, 5, 6, 7, 8 unknowns, and this is an 8 by 8 matrix, isn't it? So your what is the nature of your matrix? Is it not a very ill conditions matrix? Because most of the elements are zero. The reason is that a set of constant that is applicable for first segment will not be appearing in the third or fourth segment. As a result, those elements in the matrix entry will be equal to zero, isn't it? Every two constant will be related in such a way that only adjacent points will be coming into consideration. The distant point will not be connected. As a result, your entry in the matrix will be zero. This is a heavily sparse matrix, okay? We can solve it by using, because this cannot be solved so easily by your hand calculator. For this reason, actually, for spline type interpolation, we need a computer to handle with. But you see that this technique is very general and very useful. It is generally implemented in graphic algorithms of your computer that we usually use, okay? So just you try to redo it just for your understanding. I hope you will find some interesting something there. Then cubic spline is more complicated. We will not be going there. So with this introduction, I hope you can go further. We have left one topic related to our curve fitting, that is called sinusoidal curve fitting. Actually, we may have our data. Your data can be very changing periodically. Okay, if your data is changing periodically, can we use our polynomial type functions to represent them?
No, sir.
Then what you can do, your data can be something like this. Okay, you have a data point that is changing in this way. Okay, then what we can do, we can assume that your data is following some trigonometrical series. Okay, even some complicated form. So in that case, what you can do, when we use our curve fitting technique, in this technique, what we have done, actually, we have just for a straight line, we have done that your data can be fed by in this way, okay? Say A0 plus A1 into X plus E. This could be your fitted curve, isn't it? Then by using this curve, we calculate the error SR, and that error is the sum of what? I equal to say 1 to N. Just it is your yi, we call it y probably, yi minus a0 minus a1 xi squared, isn't it? This is the
Yes,
sum
sir.
of a square of error. Then we differentiated that with respect to a0, differentiated it with respect to a1, that gave us two equations. Then we, from that two equation, we can solve it. Now, instead of this equation, if we assume that we can represent that curve in this way, it will have an a0 value, then a1 into cosine, say omega 1, say omega t, plus say it will have another curve, say a2 into sine omega t, for example. Then what you can do, instead of using this equation, you replace that equation there and follow the same process. So with this introduction in chapter 11, something is there related to this derivation. Try to have a look, okay? Inshallah, we will discuss on top of it in the next day. This is all from my part today. Your section B